Hello, welcome. Hi everyone. Happy New Year. I hope you can all hear me okay. Feel free to say hi in the chat. I've got it open, so it'll be good to hear from you all. Hope everyone's keeping well. So we're going to be looking at trig equations today. Welcome. Feel free to say hi. Oh, cool. Yep, I'm just having a little look at the comments coming in. Cool. So what we're going to look at today is we'll go through trig equations from scratch, really, the ideas behind them, the need for identities, but also in answer to that question, generally for pure maths, what we tend to do is look to give exact answers. So that's the general kind of advice I'd give for that. This is for both AS and A level. So this topic is a year 12 topic typically, but also extends into year 13, into the full A level, and it's built on quite a lot. So it should be beneficial for both year groups today, hopefully. Thanks for your comments. I hope we're all doing okay. I'm just going to share my screen now. Hi, welcome if you just joined. Great to see some comments coming in there. Right, here we go. Hopefully you guys can see my screen. I'll just make that full screen for you and we'll get started shortly. So welcome, Happy New Year to everyone. I know it's been a bit of a strange New Year in terms of schooling, education, doing lessons remotely, and just the uncertainty of everything. But hopefully what we'll get to do is crack on with this topic today, and it'd be great to see some engagement in the chat, questions as we go. Oh no, good. I see the question there now. No, so if they specify the amount of significant figures for a question, you should do it to that answer. If they don't, I would then, as the default, give your answer in an exact form. So yeah, thank you for the comments in the chat. It's that sort of thing we'll be picking up on as we work through this today. Welcome to anyone joining. Please feel free to say hi. We're just going to get started now. So we're looking at solving trig equations. And this is a topic, as I said, that's in year 12 and year 13, a really important topic for A-level maths. What I'm going to do, just to introduce myself, I'm Max, and head of maths at SnapRevise, and I did my maths degree a little while ago now, and I've been teaching A-level maths for the past 4 years or so. So we're going to look at trig equations today, a really big topic for the A-level, and I'll try and answer questions as we go, and hopefully going through some worked examples will help people to sort of consolidate their understanding and maybe learn a few new bits if you haven't sort of touched on this yet at school. We're going to look at working out the angles by solving the trig equations, and also the importance of the domain, so the values of x or theta that we're looking at, and also using identities to solve some harder equations as well. Welcome, please do say hi and feel free to engage as we go in the chat. I'm not going to look at the use of radians, which is like the year 13 extension of this, although the actual solving part of it is very much the same process. So it should be really helpful for year 12s and 13s. Okay, so here we go. Just to start with, a bit of a recap, things we should hopefully know as a kind of prerequisite. The general sort of shapes of the graphs, which we've seen perhaps at GCSE. So the sine graph, I'm just doing a sort of sketch here, hopefully we recognise. And for those that have done stuff on domain and range, they'll recognise that the range, the set of y values, the allowable outputs, is between 1 and -1. And another key thing is that something is happening every 90 degrees. That's how I always sort of remember it. I will try and answer questions as we go, but I'll get through this, and then if we've got any specifics, I'll try and iron that out. Cool. Oh, no worries. Yeah, excellent. Good luck to anyone sitting any exams, or this is kind of a key topic. This sort of content is, as I said, prerequisite knowledge, the kind of knowing the graphs, and really useful at GCSE. But if you're not fully aware of what's going on, it's worth sort of reminding ourselves. So sine and cos are essentially translations of each other. They're both wave functions. They both look very similar, but they just shifted. And again, something is going on every 90 degrees. So if we can remember that, and remember that the range is between 1 and -1, that can really help us. Tan is the slightly more quirky one. It has what we call asymptotes, so values that are undefined. So if you put a tan of 90 into your calculator, you'll see it will say like math error. It's not defined because it's what we call an asymptote, something that it's approaching and getting infinitely close to, but never actually reaches. So some key ideas there with the graphs. But yeah, tan is the sort of slightly different looking one. Cool, yeah, hopefully we can get that, the link sent if you guys want to follow along. Obviously this video will be available after, so you can work back through it, but hopefully we'll be able to send that through. In terms of trig identities, you may have seen these before. There's two key ones we do in year 12, sine squared theta plus cos squared theta is identically equal to 1. So that's the 3-line equals, and that means it's identically equal to 1. So it's not an equation, it's not something we solve, it's kind of a fact. An identity is something that's true for all values of theta, or all values of the unknown. And the other identity we use a lot is that tan theta is identically equal to sine theta over cos theta. So these are a couple of the identities we use at A-level. Oh, welcome. Yeah, that's great. Welcome. Great to see the comments. Hopefully that link we'll be able to get that to you shortly. So I'm going to move on and just talk quickly about the different boards. This topic is common across all exam boards. So AQA, OCR, Edexcel. The A-level was adjusted slightly in 2017, and a lot of the topics have become common across all boards. So this is definitely a topic that's always been on the A-level and will be a huge topic going forward. So all exam boards cover this, and that's worth knowing. You need to be good at this skill. So we're going to look at actually solving some trig equations now. And there's a couple of different methods to this. Some people use what we call like a cast diagram. So using sine, cos, tan, and all the functions and working out where they're positive. And yeah, so this will apply to any A-level examinations, anything beyond GCSE for maths. Solving trig equations is a really important topic, so should be useful for you. There's a couple of different methods, so depending on how you've kind of worked through this content before, you might have learnt different approaches to solving trig equations. So I just want to give you a few options today in how you can approach this. So some people call this a cast diagram when we look at the unit circle and work out what's going on. Essentially, how this works is if we imagine the angle working in an anti-clockwise sense from the positive x-axis, and we take this as the unit circle with length 1 as the radius, then what we have is that for any angle between 0 and 90, sine, cos, and tan are all positive. So this sort of diagram shows us when the functions are positive and negative. And there's lots of symmetries going on here. So if you have seen this, let me know. It'd be interesting to know in the chat who's worked on cast diagrams before. Some people have done this they understand trig equations by referring to the graphs. That's absolutely fine as well. I'm just having a little look at the comments. Yes, so this will be built on in further maths. Trig equations is a real sort of prerequisite idea for further maths as well. So we'll talk through the cast method, but if you've done this with the graphs, that's great as well. So what we also know is that if the angle becomes obtuse, so here, the only trig function out of sine, cos, and tan that stays positive is sine. So the sine graph is positive for values beyond 90 degrees, as you can see. So what that means is we can use the symmetries, and that will tell us that this value of, if this is theta, if we take a right angle triangle here, then that value, the value of sine will be equal to 180 minus theta. And so what we're saying is on the sine graph, you may know from the symmetries, if you use this approach, that if we were to take, for example, 30 degrees, it would have the same output in sine as 150, which is 30 back from 180. So by the symmetry of that graph. But some people like the cast diagram because it brings all the ideas together. Excellent. Yeah, so some people haven't really explored it too much. They've just drawn out the graphs and they've used that approach, which is absolutely fine. and makes a lot of sense to a lot of people. But we're going to go through and solve some examples today using this method as well. So let me just clear that. Pen's being a bit dodgy there. Cool. So cos, and then this is clearly the sine graph. And so there's lots of different symmetries going on here. You might have noticed that what we can do is mirror kind of certain parts of the cos graph and the sine graph and work out when they're going to be negative and so on. So hopefully you've seen this relation before, that cos of minus theta is actually the same as cos of theta, because cos is actually mirrored in the y-axis, which is pretty cool. And there's also a lot of symmetries and things going on with sine as well. And you might have learnt them as all separate identities. But what we'll do is we'll crack on to actually doing some solving and check that we're all comfortable with a method for doing this. So trig functions are periodic, meaning trig equations have infinitely many solutions. I think in terms of memorizing, my own personal opinion, I would try to minimize the amount you have to learn by memory and try and understand the shapes of the graphs. I think that really helps. And what we say is there's many solutions for a given domain. Excellent. Yeah, great comments coming in. So what we're often given in the question, for those that have seen this topic before, is you won't be just told solve at A level or anything beyond GCSE. It won't just say solve cos theta equals √3/2. It will specify what values of theta you want to look between. So this is saying between 0 and 360. So if we examine that sort of part of the graph, you might notice that there's going to be two places where this could happen. So when you type this into your calculator and you use inverse cos, arc cos of √3/2, it gives you the principal value. Excellent. Yeah, brilliant. And this looks familiar to people. So what we do is we put inverse cos, because we work out when is the output √3/2, and that will tell us 30 degrees. So what you might know is that by the symmetries of the graph, you could go, right, there's another one over here, 30 degrees on from whatever that value is, and it will have the same output. And visually, hopefully, if you understand how the cos graph looks, that makes sense. Excellent. So what we've got to do is we've got to see it's 30 degrees back, from 360, or 60 degrees away from this point here, which would be for 270. So this value here, absolutely, the value we're going to get is 330. And well done to those that have got that. So we get two solutions in that given domain. And hopefully that's clear to everyone. Now that was using the graph, which was hopefully straightforward enough. But obviously as these problems evolve, this gets a little bit trickier to do. So what I'm going to do now is just talk through the kind of steps of what we just did there. So essentially the first sort of step that we did was find the first value, find the principal value using the calculator. And actually this was one you may well have recognized. It was quite a nice exact value. So find the first value. Find the first value with the calculator. So for those that are a little bit unsure, need a reminder on how to do that. Remember, the way we do this is we can find theta by inverse cos, arc cos of the output that they've given us, √3/2, the y value, and that will tell us the first answer, 30 degrees. But that's not it. And had they not restricted the domain, we know that that will carry on infinitely. So we then find the other values using the graph. And I will talk about how we could use the cast method as well, because that is really useful. But hopefully this was straightforward enough doing it that way for those that have seen it before. So what that would mean is we know from the graph and where the symmetries are happening that the other value of theta is equal to 360 minus that 30 back and we're going to get the answer as 330 as the other values. Now we are going to look at some more involved questions today, moving forward, but I think this is a good place to start. And then the key thing is to remember to answer and give all your solutions in the given domain. So write down all the solutions, down all solutions, and we will have theta can equal 30. And typically ascending order is quite good. That'd be preferable. Brilliant. So what we've got is the way that the class diagram could be used. SATC. The first value we get, all, is this 30 degrees here. Where else is cos positive in this bit, which is symmetric and 30 degrees back from 360. So I'll do more of that as we go forward. But hopefully that was kind of clear. So the method we use there using the graph would work perfectly. So we're going to go on to some slightly harder, more involved questions. For example, when we're solving a trig equation with an input of the form a times theta plus b, so a transformation of the graph, we have to be really careful and we have to adjust the range we're looking at before using the inverse function. And this is really key to this one. This is where it gets a little bit more involved. Before using the inverse function. Okay, so here's a nice example. And please feel free to work ahead of me. If you've done this before and you want to try and get there and check your answer, that would be great. So what we've got here is sine of 2 theta plus 25 is 0.2. And this time we're looking between minus 180 and 180. So this has got a few little extra bits to it we need to be careful of. So what we do first of all is adjust the range. So we adjust the interval. And essentially we're looking to solve it for theta, but this is giving us 2 theta plus 25. So what I need to do is I need to multiply and add to all the terms. So basically if theta is between minus 180 and 180, then what we know is 2 theta would be between minus 360 and 360. So what we'd have here is that's where theta would be. 2 theta would be anywhere between there and there. And the strictness of the inequality is really important as well. And so if I have 2 theta plus 20, plus 25, sorry, what I'm going to need to do is add 25 to both of those interval values as well. And so minus 335. And what I've done is I've adjusted where I'm looking for solutions. And then I can get on with the question. Brilliant. Okay, so this is quite involved, but actually the first bit is still very much GCSE. The thing we're going to do on the calculator is what you would do when you're doing like SOHCAHTOA, when you're doing right angle triangles and you're just solving to find the angle. Because the thing we do, the other step that obviously is then important, is use the calculator, as some of you have said in the chat, to find the principal value. So use the calculator, arcsine of 0.2. Let's see what that gives us. And what does that give? I think someone said it already. That gives us 11.5 degrees. So that's like a principal value, but that's a solution for 2 theta plus 25. So what we're going to do now is think about where the other solutions are going to be. Cool, so here we go. So what we've got is we found the principal value, and then we need to think about where else there's going to be solutions. So 11.5 there, and then we can think, right, there's going to be repetitions. Sorry, my pen's playing up a bit here. There's going to be another one here where it's positive, and actually potentially another one here, okay, because we've extended to 385. Okay, and then the other way, we've got a potential solution here, and we may need to look here as well. So we're looking between this interval. So what I do is I think about the rules I know, and I go 180 minus 11.5. So if I think of the cast diagram, and this was for sine, and this is going from 0 to 360. So it goes round in 90 degrees for those that have used this. And I know that my principal value is coming out there as 11.5. And then there's going to be another one at 180 minus that value. And then another one at 360 plus 11.5. So this will still be in range. Okay, if I do 360 plus 11.5, that is still in range. So 371.5 and then 168.5. No, good question. They won't ever tell you what method to use. So if you prefer visualizing the graphs, that's absolutely fine. If you're good at picking up the symmetries and things from the cast diagram, that's fine as well. But the key thing to this is that you don't lose solutions, you don't miss any out. So you have got to do this step really carefully, and the treatment of it, of finding all the solutions. Then the places that we could get it is cast also works in a negative direction. So SAT C, and obviously the places that sine is still positive are still in these quadrants, but going around in a clockwise sense is like the negative values. So that would be minus 90 there, that would be minus 180, that would be minus 270 if I work the other way. So this value here and this value here correspond to these values on the graph. Okay, so what this is minus 180 minus another 11.5. So what I'm going to get is I'm going to get, so you could do it that way, or you could think of it as 168.5 minus 360, and we're going to get minus 191.5, and then carrying on as well, the final one minus 360 plus 11.5 would correspond to this one. So what we will get there is minus 348.5. So these solutions aren't my final answers. Can anyone suggest like what we need to do with this? So I've got 4 potential values coming out that are in range, that are acceptable. Oh no, sorry, 5, because I had 11.5. I found an additional 4 values that are still in this correct interval for 2 theta plus 25. Can anyone suggest what we need to do with those? Right, exactly. These are solutions for 2 theta plus 25. Great, I don't want to solve for 2 theta plus 25. I want to find theta. So I've just got to kind of undo that little transformation, that little shift. And I'm going to do that now. So what I need to do, absolutely right. Yeah, brilliant, is subtract 25 and then halve it and then divide by 2. Because essentially my solutions here, these are actually, that's not correct. That should be 2 theta plus 25 is equal to all of these. And I don't want 2 theta plus 25. I just want theta. Oh, excellent. Yeah, if that's not a way you've done it before, I'll clarify that. That's really interesting. This bit here on the cast diagram, you can actually use cast the other way around to represent negative angles. That's what it's good for as well. So going in the anti-clockwise sense gives you the positive angles, but actually if you treat that line as 0, just picking up on that comment in the chat, if you go in the clockwise sense, then you're going minus 90, minus 180, minus 270, minus 360. So going that way deals with the negative angles, and cast can work like that as well. So it's really powerful in that the anti-clockwise sense gives you the positive angles and the clockwise sense gives you the negatives, but it works for both directions. So if you haven't done that before, it actually does work really well like that for those that have practiced it. And thank you to the answers coming in the chat as well. That looks brilliant. So what I do with each of my values is I take my 11.5, I subtract 25 and divide by 2. And so one of my first solutions I get minus 6.7, and I think that agrees with what we're perhaps getting in the chat. Take my next answer, 168.5 minus 25 over 2. and I get 71.7. Good. And I do that for each of them. And I get 173. And I do it for my negative one as well. And as I did say, actually, it'd be better if we wrote it, the final answers in ascending order, but that's fine while we're working them out. Minus 108.2. So they're my solutions for theta. So theta can equal minus 108.2. And well done if you got that. So this had 4 solutions to this question, 71.7. And finally 173.3. Very well done. Yeah, lovely. That's fine. Cool. So some people use the graphs and some use cast, but you should definitely show what 2 theta plus 25 equals and then what theta equals, just so you've shown the full marks to get all the work in. The difference with A-level is you do get method marks and you do need to see a method. You can't just jump to the final bit. Hope that's okay. Let me know in the chat just to give me a quick indication whether you've shared answers or not. Maybe you're just watching this for a bit of revision, but feel free to write a 1, 2, or 3 in terms of how difficult you're finding it. Hopefully no one's super confused, but be honest. Straightforward, hopefully, or maybe it still needs a little bit of practice. But that'd be great to know. And thank you for all the comments and questions and answers that we got there. That's brilliant. Well done, guys. Lovely. Right, I'm going to carry on. So we've got another question here. Again, feel free to work ahead of me this time with this question. So tan x equals minus 3 in the interval 0 to 360, giving your answers to the nearest degree. Okay, so I might start with the approach that those drawing the graph might use. So we're looking at the tan graph from 0 to 360, and we know that the asymptote's at 90. Let's have a little look. So a little sketch. And it's kind of like that. And then there. And then like this. Okay, so what we've got is from the calculator straight away, if we do inverse tan of minus 3, we get a principal value, a solution of minus 72. So to those that got that, that's great. The problem with that is it doesn't lie within our bounds. So it's given us a value over here that's out of range, minus 72. And you might think, right, but I know kind of what that aligns with. So you might go, right, I'll trace it across, and there's going to be a solution here and a solution here that will be in range. And that's 90 degrees, that's 180, that's 270, and that's 360. And to those that use the graphs, you might go, well, the symmetry is it's 72 away from 0, so it's 72 back from 180 and 72 back from 360. If you guys can see that, that might be the method you use. And that's absolutely fine. That's like a lovely way to approach it. That's fine if you like drawing the graphs and you like doing it that way. That's brilliant. So you might go, well, I can do that now. I can work that out really quickly. And so what you'll do is you'll go that first value, if you imagine that was theta naught, the first solution we're going to get here, and the second solution we're going to get here, is it's going to be equal to minus 72, add 180, or 180 take away 72, and so you're going to get 108. Well done if you got that. And the other solution is going to be that value taken back again. So what we've got is 360 minus that value, and so you're going to get 288. Okay, as your 2 answers, and well done to anyone that got that. And the other solution, well done if you worked it out, is tan. You can just keep adding 180 degrees because it repeats every 180. And that can be seen if you do use the cast diagram, SATC. Now what we've got is tan is negative, and the principal value that gives you negative 72 would put it in this quadrant. Because if that's 0 and that's minus 90, minus 72 is somewhere down here. Obviously, I've not drawn that accurately. It would probably be more like that. minus 72. Now, where else is tan negative? Well, not in T and not in A, so in here. And so that would be sort of the same sort of size. So what you'd get is you'd get the negative value there, or in terms of the positive direction, because we're working from 0 to positive 360, 72 back from 180, and 72 back from 360. And that's how we could use the cast diagram. So it does work for negative answers as well. And someone asked a really good question about that earlier. Thanks very much for those submitting answers in the chat. This is really good, but do ask questions as well. If you want to clarify, that's absolutely fine. Let's keep going. So we'll do another one now. This one is solving between 0 and 180, inclusive of 0, but not of 180. And there's a bit more going on with this one. Answers to 1DP, it tells us this time. So again, feel free to work ahead of me. And then we're going to look at a few questions that involve trig equations, where there's perhaps a quadratic element to it, or also an identity is needed to be used. So let's try this one. So for this one here, what we're going to have is, let's start it off and think about what we need to do to our interval. Now, I would say let's think about 0, or theta is between 0 and 180. So what we know, if we do it all in one step, double it and take away 30, 0 times 2 minus 30 is minus 30. And double 180 and minus 30 is 330. So we're looking, oh, not 336, 330. So we're looking for solutions within that sort of interval. Now, what we're asked here, it's a little bit, it can put us off a little bit further sometimes, is we're asked for sine of 2 theta minus 30 plus 1 equals 0.4. So the plus 1 is a little bit annoying. So what we can do here is subtract that, and that would be the same as solving that this is equal to minus 0.6. And so then we can get on with the question as we had done before. Use inverse sine of minus 0.6. Well done, yeah, excellent suggestions there. And start solving for 2 theta minus 30. So what we'd do is we'd subtract and we'd get the principal value, so 2 theta minus 30, and you're going to do inverse sine of minus 0.6 is going to come out as, whoops. The first value, let's check if we agree. I believe it comes out as minus 36.9. Do we get that? Do we agree with that one? Now, again, that's out of range. And you can use the cast diagram, again, absolutely, or you can use the graph. So for those using the graph, what we've just found is the value that's come out is down here. So if we imagine the graph going up to that point, we're cutting it off at 330, but we are starting it at minus 30. And the solution it's come out with in our calculator is minus 36.9, which is out of the range we wanted. So we do know there are other solutions over here and over here. So we typically get 2 solutions. Those using the cast diagram, let me redraw that, which is absolutely fine. And feel free, as I said, to work ahead of me and find the solutions here. S, A, T, C. The first value is negative. When is sine negative? Because we're looking for sine being minus 0.6. Sine is negative in here and in here, because it's positive in here and in here. And that agrees with what we got. The principal value came out as minus 36.9. So we sort of know the size of that bit. So I know where the solutions sort of reside in terms of the quadrants now if I'm using cast. And because I'm looking from minus 30 round to 330, if I think about that, minus 36.9 is beyond that boundary. But going from 0 round to here, this is 36.9 added on to 180. And also this solution round here would be 36.9 back from 360. So we've got our 2 solutions that are allowable. So what we get, and well done if you got this, thanks so much for those that have been sharing answers in the chat. we get 2 theta can be minus 30 can be equal to 93.4. Oh no, sorry. 2 theta minus 30. So we're going to do our 180 plus the value we had, plus 36.9. So we're going to get our two values. So we're going to get 216.9, and also the one which is 360 minus that value, 36.9, if you're using the size of the angle and you're using cast, and that would be 323.1. And then for those that have finished this question off, which is great, what you need to do is you need to subtract 30 and divide by 2. And I think we're going to get theta out as 146.6 and 93.4. Let's just check that. Let's just check that works. So we're going to, oh no, sorry, we're not. We're going to add 30, aren't we? So those values are wrong. We're going to add 30 and divide by 2. So I believe we're right there. 123.5. Yes, excellent. Thanks for the correction, guys. Just checking everyone's on their toes. That's good. Well done. And well done to those that have already submitted that. So 216.9, add 30. Let's check it, divide by 2. Yes, excellent, absolutely right. So 123, and I'll try and answer questions as we go. I'll just get these written in. 123.5 and 176.5. Very well done. So good questions coming in. This content is for AS and A-level maths. It's this part of it is in year 12, but it does extend on into year 13. The idea and the actual process, and it builds and builds, and it will come up in further maths as well. It's a really constantly growing idea. So this is the start of it really, but we start to work into the use of radians. We also start doing much bigger contexts with trig modeling examples. So you'll see that a lot more in year 13. And as I said, it does overlap into further maths as well. Further maths, there's a lot more breadth to kind of new topics. Just to answer the questions there, how did we get this one? Good question. So this value is kind of corresponding to the part here on the graph, which is 36.9 back from 360. So that's one way you could think of it. Or if you're using cast diagrams, it's 36.9 back from 360 there, because that's the other place that cos is negative. Oh, sorry, sine is negative. So you can either use the graph and go, it's that bit back from 360, or that amount on from 180 if you use the graph, but also it works from cast. So hopefully that's answered your question. But yeah, brilliant question and worth clarifying things like that. So what we're going to do now, this is where it gets a little bit more involved, but it's quite a nice one to look at, is using things like identities and extra kind of little steps that can help us. So for equations involving multiple trig functions, we can basically rearrange, and this helps us out, and this is something that really extends into year 13 as well, into A-level, rearrange using trig identities. So have a little think, for those that have done these before or seen trig identities, you might be able to anticipate which one we're going to use, but we can't really solve it until it's in terms of one function. So identities. So for example, the two we said are tan theta, which is sine over cos, and one being identically equal to sine squared plus cos squared theta. In answer to that question, I'm not, as far as I know, that we'll be doing further maths topics in the near future, as far as I know, on some days, although obviously the maths content very much feeds into that, but it's something we could maybe look at and explore and find out about. But obviously these sessions, I will talk a bit more about SnapRevise and what we have to offer separately at the end, but these sessions are very much geared up for focusing on the single maths A-level as a key thing really to start with. Right, great, well done for those that have rearranged this. I think we might have noticed that the key identity that we're going to use here is actually the one involving tan. So if 4 sine theta is equal to 3 cos theta and we're asked to solve this, A lot of people, by mistake, go to rearrange this. No worries. Good luck with any exams coming up. That's absolutely fine. And thanks again for all the comments. So 4 sine theta is equal to 3 cos theta. What we're going to do here is just a bit of division. So if you divide both sides by 4, we would get sine theta is equal to 3 cos theta over 4. And if we divide by cos theta, we get sine theta over cos theta. And this is really a case of just spotting the identity is 3 over 4. And that is actually equivalent to tan. So now it's just got one trig function that I need to solve. So tan theta is 3/4. So that's what I'm solving. So I do inverse tan of 3/4. And I get my principal value out, which comes out as, I think, 36.9 again. Yeah, absolutely. That's right. So we've got a few more questions we'll try and get through, and then I'll be able to answer any questions as well as we go. So again, let's think about the tan graph. And again, if you like using cast, that's absolutely fine as well. So the value it's found for us is tan is equal to 3/4. I've not drawn that particularly accurately there. Let's say that's 3/4 very roughly, and that's 36.9. And there's going to be another repetition of that over here, 180 degrees on from that value. Okay, so what we're going to get is our two answers is 36.9, and then add 180 to it, and we're going to get 216.9. Very good. Well done, and thanks to those that got that. Welcome if you're just joining. Hopefully this is making sense and this is working well for you. Yeah, well done for getting that other value as well. And that is really crucial. So GCSE style, where you just find one answer, is no good anymore. We need to look out for all the potential answers in the given interval that we're looking at. Well done. So we're going to do another kind of slightly quirkier example. This one here. So we can solve equations involving squared trig functions by basically how you would solve a quadratic. So by factorizing, if that's possible. So by factorizing, make sure I spell that right, or using the quadratic formula. And actually for those that are using the class Whiz or some of the newer calculators, they actually do solve quadratics for you, which can be really handy without you needing the formula. So there's a function that just solves quadratics. You just type it in, which is a good help for ones like this, where they're like disguised quadratics. Brilliant, really good suggestion. And previously we did a session on disguised quadratics, one of the Sunday sessions, and we looked at using a substitution. So superb suggestion there. And we might want to call it y or x. So I'll go with that example. That was brilliant. Let's let y equal to cos theta, because what this whole equation would boil down to would be 2y squared plus 5y minus 3 equals 0. And it's a lot easier for us to get started now, because it looks like a quadratic, and it is a quadratic. And we can go, right, can I factorize that? And this quadratic does in fact factorize. 2y minus 1 y plus 3 equals 0. And from that, we have two potential solutions. This one here, that y is minus 3. And this one here, that y is equal to a half. And do ask if you're not sure how I've done any of that. But what we've done is we've kind of ignored the trig aspect of it for a minute and thought, let's think about replacing cos with y or x, so we can see the quadratic side of it, factorize it, and then look at where the solutions are going to come from. Superb. So really good suggestions. Now we're putting cos back in. Cos is equal to, cos of theta is equal to minus 3, or cos of theta is equal to a half. And well done to those that noticed that cos can't equal minus 3. That doesn't work. The cos graph, the most it ever is 1 or minus 1. That's the range. So minus 3 will say calculator error, math error, when you try and solve that. So that's brilliant. So that's impossible. So we're focusing on this one solution set of cos theta equals a half. So you find your principal value by plugging it into the calculator, inverse cos of a half, and then you just look for other values in this interval. And to those that have done that, very well done if you have. Looks like some of you have already. We get theta as equaling minus 60 and 60. And remember, that makes sense because cos is symmetrical about the y-axis. So very well done if you've got both of those solutions in that interval there. Great. Right, a little quick checkpoint. I'm trying to keep an eye on the chat as well, so please do ask questions as we go. And what I think we'll do, I think that was really good. I'm going to just check how we're doing. So if you found that okay, give me a little indication of it. A 1 if that was fairly straightforward, 2 if it's kind of still needs a bit of work, and 3 if it's still quite confusing. Thanks for that. Thanks for that interaction and letting me know. It's good to kind of get the feedback so I know as I go, but you've been brilliant asking questions and also sharing your answers, which has been great. Yes, minus 60 is one of the solutions. Thanks, guys. That's great. Just to backtrack to clarify that here, minus 60 was an answer because the interval is between minus 180 and 180. So when you put it in your calculator for cos, which looks like this, when is it going to equal a half at this value and this value? 60 and minus 60. So they are in range, so hopefully that's helped. But yes, minus 60 is valid because we're looking between minus 180 and 180. Sorry, I should have sketched that on, but thanks for asking. Lovely, well done. So they are both valid solutions for this question. Very good, cool. I'm gonna keep going. So what I think I'll do now, this video should stay on here, yes, so you can watch it back or double check it after. But what I'm going to quickly do is, I think I'll skip ahead for a second just to kind of remind us of where we're at. I'm a bit mindful of the time. We've looked at trig functions, all the prerequisite knowledge of the graphs, the trig identities, the shape of the graphs, and also the cast diagram for those that have used that before. Understanding how to use the inverse function to get the principal value out of the calculator. And also how important the domain is. And this grows, this becomes more important as we go through, especially into year 13. And we start looking at radians and other things as well. And also identities and quadratics come into this as well. So they love to link topics together. But if you have a really sound understanding of the process, what am I doing? I'm solving this trig equation. I'm going to use the inverse function, see what other solutions can be generated and adjust them if necessary. That's the key thing we're doing here. So hopefully that's worked out, that makes sense to you all. What I'm going to just mention now is if you have any questions, keep them coming in the chat. I'm going to just quickly talk about SnapRevise and some of the other things because people were asking about further maths, other subjects. So I'll do that as well. This video will be on this channel yet once the session's ended. I'm just going to stop sharing that there for a second and hopefully reshare something else. So do keep the questions coming in, that's absolutely fine. I'm going to now just quickly talk you through SnapRevise, the platform and the resources that are available. So hopefully you can see my screen. I've just gone on to the SnapRevise site. And what we've got is, for those that haven't maybe explored the site before, for all your courses, there's a great deal of revision tools, resources, diagnostic quizzes, and web classes that are live, a bit like this one. So for example, I've got some web classes tomorrow, and there's a whole schedule and previous web classes on here as well. So we look at all aspects of the A-level maths. We do the pure maths, we do the stats and the mechanics. So on a Monday, there's year 12 web classes, followed by a drop-in. So if you've got questions for homework or mocks coming up and you want to ask me a specific question and you want me to run through how to do it, we have the drop-ins for that. And we also have year 13 sessions on a Wednesday. So they're all scheduled, they're all uploaded, and they're all on the platform for those that find it useful to have some tailored content and help with their work in school, especially at the moment where it's all quite remote and you might be feeling a little bit on your own for that. And this will work for A-level. There's a variety of courses. So if you look for your exam board, it's not just for Excel, AQA, OCR, all the exam boards, you can check it out on our platform. And material is tailored exactly to that exam board. So you can pick a topic, you can do mock papers. So these are resources that are geared up for this brand new A-level, and start little quizzes that then generate revision for you. And there's some excellent printable resources on here. So if I just guess these quickly and skip through, and it kind of works out how you're getting on, and then it tailors your revision to that. So the platform is really powerful, and there's lots of different materials and different tools on there. But the revision resources, I want to just make a point on. As I said, I'm just rushing through this diagnostic quiz to sort of show you how it works, but it will look at how you've answered the questions and will tailor the revision to what you understand and what you need to work on. So it's a really powerful tool. But as I said, there's live sessions, there's drop-ins, and there's opportunities to ask and learn specific topics if you haven't been taught it, or you want to get ahead of the game, or also you just want to revise and look over something. So this is the site, and then what it will do is work out what you know and what you maybe need to work on, and then it will take you to different points in a really nicely made revision video, and you can jump through the content and answer any questions that relate to that bit, and the specification points are tailored exactly to what you've struggled with. So this is a really important point, particularly for those looking for resources online. Lots of people use websites that have all the old A-level material, past papers on, and I always say be careful with that, because actually you need to make sure it's relevant for the course you're currently working on. And where there's been so many changes, it's really important that you're not learning stuff that's out of date and not on the course anymore. And everything on this site is bang up to date and tailored to all the different exam boards. The revision guides are really clear, printable, lovely revision resources that I know A-level students like and need a lot of the time. So really good for you to have a little explore of that, as I said. And then every topic is broken down and all the specification points. I'm just having a little look in the chat to see if I can answer questions. Thanks very much for the comments, guys, and taking part so actively in the chat today. That's been brilliant. I'm just going to stop sharing that for a moment and reshare my PowerPoint with you. And just so I suppose the final things to say is, if you have found this useful and you are interested, do look on the site there. We will have more of these sessions coming up. So what we've got in future is the YouTube sessions for maths, physics, chemistry, and biology, and they're happening over the next few weeks. So set reminders, do check those out, and obviously you can watch them in the ones that have happened as well. And that's great. And a lot of you, I know, I'm aware of a lot of people doing the sciences and the maths, they kind of complement each other. So you've probably got a very full-on schedule of revision and work to keep on top of. But hopefully these sessions will help you. In addition to that, we have got a discount code that will expire tonight. So yeah, some of you have anticipated that. So this code here will give you £10 off your first month if you do want to sign up to the platform and look at some of the other resources we have on offer. So maybe make a note of that if you're interested to try it out. That would be great. As I said, thanks very much again to everyone that's taken part so actively throughout the session today. And we will have another one coming up shortly. And hopefully you'll find it useful for your other subjects as well. So I'll stop sharing that there. And if there are any questions, I'm just going to check back in the chat now to see if I haven't missed anyone. But as I said, solving trig equations is huge. It's such a big part of the A-level maths course, as is the calculus, differentiation and integration. But as we see working through year 13 towards the A-level, a lot of these topics come together. So you can't really afford to have any major gaps in any of these big topics because they start to feed into each other. Modelling is now a huge part of mathematical modelling is a huge part of the A-level. And in light of everything that's going on this year, mathematical models, we can understand how important they are for predicting things and, you know, calculating within the realms of health service, finance sector. And it's really been a real focus in the change of the A-level in 2017 that mathematical modelling is given some serious consideration. And using trig equations really feeds into that. Okay, right, well, hopefully we'll be able to help you out with that. There are colleagues you can contact obviously about that, but it would be great to see some of you at these YouTube sessions in future, and of course also in some of the web classes and drop-ins that we're running throughout the week. They are really geared up at helping you and helping to support you through whatever you're doing at school. I know a lot of you are having to work quite independently at the moment, and I really feel for anyone in year 11 and 13 and 12, obviously, that are kind of a little bit uncertain with what the next few months are going to look like. The good thing we can be certain about is that the content is very much fixed. We know what the A-level comprises of, and we've got resources built to help you and support you with that. Excellent. Thanks very much again, guys. Keep well and good luck over the next week with all your studies and revision that you've got coming up. Thanks again for working so well in the chat and communicating with me regularly to let me know how you're getting on. And yeah, have a good rest of the week. Take care and speak soon, hopefully. Well done, guys.